So chapter 5, we're going to be looking at biomes and biodiversity. So we're going to be actually breaking this one up into two different sections. So we've already kind of looked at sort of the process with which different organisms are going to adapt to give us that biodiversity. But in this chapter, we're going to focus more on sort of the areas in which those organisms reside and sort of the differences between those different types of locations. And then we'll move into sort of the threats to those locations, how that endangers the organisms in those locations, ultimately the ramifications of those sort of events, and then also how we can sort of address it and combat those issues, hopefully help maintain the biodiversity of the planet. But with these, we want to just define the biomes. You can kind of see it in this picture here, just going to be the different types of regions, and we're going to go through and actually define the different classes and see how we sort of separate out these different types of locations. But based on the differences in those locations, we're going to get the differences in those organisms. So since the organisms adapt to the environment they're in, the differences in those environments are going to be crucial in terms of what type of biodiversity we see in that location. And then to start, we're going to be focused on the terrestrial biomes, so the ones that take place on land. So you can see just kind of on the examples we have here. This isn't an exhaustive list, but you can see the ones sort of on the left-hand side, most of them. Those are going to be the terrestrial ones, the ones on land. But then we'll move into marine, so focusing on the saltwater environments, and then we'll finish up with the freshwater ones, so things like rivers and lakes and stuff. Like I said, terrestrial, just referring to the Earth. So we're going to be looking at the land-based biomes in this case. And with these, there's going to be a whole bunch of them. We're going to go through, I think it's 9 of them, depending on exactly where you look. Sometimes they get broken up into just slightly different categories. So depending on the exact source, there may be a slightly different number of total biomes. They may be categorized slightly differently, but traditionally we're going to see kind of these main 9 terrestrial biomes. And with these biomes, you can kind of get an idea of it from the graph here. We've got precipitation on the y-axis, temperature on the x-axis, because those are going to be the 2 key features in determining what type of biome a region is going to be. So just looking at this quick before we start to go through each of them sort of individually. If we look at the bottom left corner of this graph, so this is going to be the coldest, and it's also going to have the least amount of precipitation. So this is going to be where we're looking at tundras. So those are going to be kind of the very northern and southern points of the Earth, or very high up in the mountains. They're going to be very cold, very dry locations. So because of that, they're not going to be as biodiverse as the other biomes we see. And then the other extreme, the top right, now we're looking at the warmer temperatures. We're looking at the wettest environments. Those are going to be the scenarios that provide the most biodiversity, and that's what we see in places like the Amazon rainforest. And that's why we'll ultimately talk about, we've already seen it a little bit, but we'll talk about it more. Protecting the Amazon rainforest is extremely important because it is such a biodiverse area. And then just based on this biodiversity, just think about it, these are going to give us the different types of environments. Those different environments are of course, going to have different characteristics. So the more diverse that area is going to be, like we saw in earlier chapters, that means it's going to produce more biomass, so it's going to be more productive. And then in terms of resiliency and stability, it's going to be more able to withstand stresses, different stresses from the environment, whatever it may be. Could be a weather disaster, things like that. And it's also going to be able to better reestablish itself if something does kind of destroy part of that ecosystem. And then with these, we should note these are going to be sort of in the absence of human disturbance. So of course, humans can go in and then change some of these landscapes. So when we're looking at kind of defining these different biomes, we're thinking of it in terms of if humans kind of never alter that area. And then with these, again, we've seen these terms in previous chapters. I want to say chapter 2, but I'm not great at remembering exactly what chapters they are. But productivity, just the production of that biomass. Resiliency. So if a stress is introduced to an environment, something that may potentially be a negative outcome in that environment, the more resilient it is, the more resilient that biome or that environment is, the better it's going to be at sort of withstanding whatever that stress is. So the more resilient, the less likely it's going to drastically change when that stress arrives, basically. And then stability, if a major event does occur, so something like a forest fire, a flood that kind of comes in and washes out a large piece of that environment, the more stable it is, the more able it's going to be to reestablish itself, return to kind of that previous state. And one example of this, like we said, we focus on those extremes, tropical rainforests versus the tundra. If we go a little less extreme than the tundra, we think about just the forests in northern Canada. So forests in Canada versus the Amazon. There's going to be issues if we deforest both of them. Obviously, that's not going to be it's going to provide timber, but it's going to have negative environmental consequences as well. But when that occurs, because the rainforest is so much more productive, so much more biodiverse, it's going to be better able to withstand that change. So when the Amazon rainforest is cut down, part of it's removed for whatever reason, it's still going to take a long time. And like I said, it's still going to be something we want to try to avoid if we can. But in that environment, it's going to be more productive. So it's going to be better able to reestablish itself and sort of return from that deforestation. Whereas the northern forests, they're going to be less productive. They're going to be less resilient, less stable. So it's going to take them much longer to kind of regrow and replenish themselves. And that's if they even do it. So sometimes in the very north, depending on exactly where it is, the conditions based on the weather and the actual sort of environment it's in, soil and other factors, that forest may not even be able to reestablish itself. Whereas the Amazon, again, is going to take a really long time, but it's more likely that it will be because it already has that increased biodiversity. So it's more likely to reestablish itself. And then before we kind of jump into the specific biomes, like I said, we're going to be focused on temperature and precipitation in terms of kind of explaining what we see in these different types of environments. And what we can do is visualize this with these climate diagrams. So in the textbook, there's a couple different examples of these. And essentially what it's just showing is on the left-hand side, we've got the axis for temperature. That's what we're representing in red. So it's just showing how the temperature changes over the 12 months. Similarly, on the right side of these graphs, we've got the precipitation. So that's going to be the blue dots, showing how much rain and snow and different things we're getting in those different months. And then if you look, we've got on the right two graphs, we only have blue. One of them, we've got a little darker blue. But on the left graph, we've got some yellow mixed in there. What these are showing is just basically the net movement of water almost. Because when it's blue, that means precipitation is going to exceed evaporation. And then when it's dark blue, it's just because those are going to be months where we have a whole bunch of rain. So you can see the scale just changes there. They just use the darker color to kind of note that. So we go up by 20s initially for the precipitation, but then when we get near the top, we go up by 200. So just to distinguish that, that's why we've got the darker color there. But in all of these blue months, what we're seeing is more precipitation than evaporation. So those are going to be kind of rainier. Even the higher temperatures here, we're still going to have enough rain to overpower the amount that's evaporating. So these are going to be the wetter months. And then the yellow is going to be the reverse. That's going to be when we have more evaporation than precipitation. So those are going to be the drier months. And we can use this to explain sort of what we see in different locations. So for example, the first one here, looking at San Diego, so Southern California, we can see kind of at the turn of the new year, January, February, maybe a little bit of November and December. That's going to be when we have more rain than evaporation there. And if you look, the temperature doesn't change too much. We definitely get a rise in the summer months, but the big thing about this is going to be the drier climate. And this helps us explain why we see forest fires in California and other similar places in those summer months, because what we're getting is the warmer temperatures. 20 degrees Celsius, by the way, is approximately 70 degrees Fahrenheit. So we're getting a little bit warmer there on average. And then the big thing is we're just having sustained dry months. So the drier the months, the drier the trees and the forests are just going to get, the more naturally ignitable they're going to be. And that's just why we're going to see more forest fires in those months. And then with this, what we're also seeing due to global warming and climate change, we're seeing these graphs actually change a little bit. So what we're seeing is the amount of evaporation that's occurring is increasing. The amount of precipitation is decreasing. So the extent of these dry periods are becoming more extreme. And that's why we're seeing more and more forest fires pop up throughout the Western United States. And it's even starting to move sort of to the Eastern coast as well, in terms of some of the smoke movement travels throughout the atmosphere, but also we're seeing sort of this process occur a little bit more on the East Coast as well. And then I'm going to skip the Philadelphia one for now. But then when we go to Brazil, we're looking at the rainforest, and that's why we can see it's close to the equator. So that's why we see the temperature is pretty constant. Near the equator, you have more consistent weather. The further away you get the different extremes, because now you're going to get more of the seasons due to the tilt of the earth. But with the Brazil case, we can see all of these months are going to be exceeding evaporation. So we're always going to have more precipitation. We're always going to have sort of an input of water. And that's why we're going to see in these rainforests, we're going to see such a productive biodiverse environment, because we've got this fairly warm climate, but we're also providing a whole bunch of water to these environments. So that's going to be two conditions that are going to help support growth. And then in addition to temperature and just precipitation or moisture, what we can also look at is the latitude of these locations, and kind of use that to explain what we see. And first, what we have is just the reason we call the tropics, the tropical rainforest, things like that. The reason we call it the tropics is just because it's between the Tropic of Cancer in the northern hemisphere, the Tropic of Capricorn in the southern one. So anything between those latitudes is going to be referring to the tropics. But what we can see in this graph, if you look, or image, I should say, if you look left to right and just go straight across any of it, you typically see there's going to be changes. So if you look across the equator, we see mostly green in South America, a little green. We get some of the savanna, more green. So you can see most of it is green going across the equator. That's where we've got our tropical rainforests, because that's going to be the location that provides enough rain, provides the correct temperature as well. So that's the environment for those rainforests. But then when we go to the northern hemisphere, if you look stretching across North America, parts of Europe into Russia as well, we see this coniferous forest, because what we're going to see based on these latitudes is just bands of these different biomes. And that's because at these different latitude, or at the same latitude, I guess, going across, we're typically going to see similar temperatures, with the exception of if it's a mountain location. In that case, we'll see the temperature is usually going to be less than a similar latitude. But if two locations have the same latitude, similar elevation, we're going to see similar temperatures. And again, that's why we see sort of the coniferous forest stretching across the top part. And then even above that, we see the tundra. And again, we've got the rainforest kind of stretching across the equator region. And we see something similar with the temperate grassland kind of in between those two locations. And then, like I said, if you're at the same latitude, same elevation, you're likely to have a similar biome because it's likely to be a similar temperature, at least if it's if the precipitation levels are the same. If one of them's a much wetter location, one of them's much drier, obviously that'll also come into effect. But what we can see is changes in these biomes based on elevation as well. And one example of this is just going to be a 60-mile stretch, so 100 kilometers if you look from Fresno to the top of Mount Whitney, which is I believe it's the tallest location or the highest elevation in California. But it's about 100 kilometers between those two locations. That's about 62 miles. And then between those two locations, you also have a very pretty drastic change in the elevation. And like I said, what we're going to see in the changes in the elevation is we're going to see changes in that environment, which is going to give us different biomes. So as you were going from Fresno to the peak of Mount Whitney, what you'd see to start is you're going to see, and we're going to cover these kind of as we go through them individually, but you're going to see the environment is going to change pretty drastically from sort of a almost deserty environment in Fresno to a much greener environment as you start to move higher and higher in that mountain, because what we're going to see is the temperature is going to change, the amount of precipitation is going to change as well. So we're going to see hotter, drier climates near Fresno, and then as we go into the mountain, we're going to see cooler and wetter environments. So that's why we're going to actually be able to start supporting trees. We're going to start to see more of the we're going to see a more productive, a more biodiverse environment there. And then this is called vertical zonation, by the way. We can see something similar here, just with a different image. And then just to backtrack for a second, I did say we're going to see it get more biodiverse as we go up. Based on what we're kind of seeing here, that makes sense. It may at some point reach sort of a limit where it'll actually start to go back down. Because if you keep going up, eventually you're going to reach a point where it's just going to become too cold and it's going to become snowy. So it's going to become that mountain environment, and things can still survive there, but it's going to be much more difficult for them. So rather than saying it's going to get more biodiverse as we go up, what would be a better way to say that is really the biodiversity is going to change as we go up, because we're going to see different biomes at these different levels. And then that's going to be due to the changes in the temperature, changes in moisture levels of precipitation. And then if you kind of just look at this image, that's also going to affect the resource distribution. So if we look at the middle here, this forest is going to provide much more resources than the tundra will. And that comes into play with the temperature, the precipitation, but that's something else you want to think about in terms of the biodiversity of these different locations as you change with elevation. But the first biome we're going to look at is going to be the tropical rainforests. We've already looked at these a little bit in some of the previous chapters, but these are just going to be, and we already saw it a little bit with that climate diagram. They're going to be fairly stable locations in terms of the temperature, as well as the precipitation. So they're going to constantly be getting rain, and that's going to help support the different the growth and the biodiversity in those locations. So they're going to be extremely biodiverse. And then with these types of forests, one type, and there's going to be several actually different types. We're not going to go through all of them. With this, just because there are so many different biomes and we kind of have to cover all of them, we're not going to go into great detail about it. One thing you can do actually, though, is if you have access to whatever streaming service Planet Earth is on, if you kind of actually just go through and watch some of those, obviously you're still going to want to look at the other resources for this course, but if you're interested in sort of one biome specifically, those do a pretty good job of kind of looking at some of the different aspects, the different organisms, and the relationship between those pieces within those different types of environments. So you could watch those and it could kind of be homework. But with these, the cloud forests, you may have seen pictures of these. These are going to be rainforests higher up in the mountains, and they're going to be they're going to have the characteristic of clouds. So they're just going to have constant moisture, constant fog around, and that's going to keep everything extremely wet at all times. And then these forests are also going to be slightly cooler than the rest of the rainforests in this region, this type of biome, just because they are going to be at that higher elevation. And then the tropical rainforests are going to be what we typically think of when we think of like the Amazon rainforest and things like that. They're going to be the more consistently warm locations. They're going to have that very high level of precipitation as well. And one thing that's kind of interesting about these types of rainforests is that the nutrients themselves. So we've looked at different nutrient cycles in chapter 1 or 2. And traditionally, or typically in a lot of environments, the nutrients are going to be located in the soil. What's interesting about the rainforest, though, is that the nutrients are actually located in the living organisms. So what occurs in these rainforests in order for new plants and new organisms to grow, for things to survive, is whenever something, whether it's a plant or an organism, whenever it dies, it's going to fall to the bottom of the rainforest, and it's immediately going to start getting decomposed, and the decomposition is going to happen extremely quickly, just so that the nutrients can be recycled back into the plants and kind of get back into the system. Because again, with the rainforests, pretty much everything is going to be, or at least in terms of the nutrients, is going to be located in those organisms rather than from the soil themselves. So it has to be a very quick decomposition. Otherwise, there's just not going to be anything available to support the different plants and the growth and stuff like that. And one thing, and because of that, it makes deforestation even more problematic, because if we remove the trees, the other organisms living there, because of the habitat destruction, we're now removing those organisms. We're now removing the nutrients from that soil, or the nutrients from that area, I should say. So now there's not going to be anything to recycle in that area. There's not going to be as much falling to the earth, decomposing and getting the nutrients back that way. So when we do clear these areas, whether it's for just strictly mining, so just removing the trees, or whether we're clearing them to, or I should have said logging rather, not mining. So whether it's logging just to remove the trees for whatever use that may be, mining for different substances. Sometimes they get cleared just to create land to grow crops for agriculture. But whatever the reason may be, when we're removing these trees, we're removing that biodiversity. We're also going to be removing the nutrients from that area, and it's going to make it more difficult for the plants to regrow and for that environment to reestablish. And then with these, this just shows a couple of different areas along the equator that are going to have similar biomes, because they're going to have similar environments. So we can see they all have very constant, very consistent temperatures, because again, they're all located near that equator. So Brazil, Zaire, and Malaysia, you can see where they're located on this graph. And then they have different levels of precipitation throughout the year. Malaysia and Brazil are fairly even overall, even though there's a bit of a difference in sort of how they get that rain. Zaire a little lower, but they all do have pretty constant, pretty extreme precipitation. So that's why we're going to consider all of these to be sort of in that tropical rainforest class. And then the second part of this chapter, what we're going to do is look at sort of the consequences of biodiversity loss, or at least sort of what leads to it and how we can combat it. But one thing about the Amazon rainforest in particular is it is such a extremely biodiverse area. And you can just get an idea of it. I took this from Nat Geo, but tropical rainforests are the most biologically diverse terrestrial ecosystems in the world. The Amazon rainforest is the world's largest tropical rainforest. It is home to around 40,000 plant species, nearly 1,300 bird species, 3,000 types of fish, 427 species of mammals, and 2.5 million different insects. But then when we remove these areas, when we log them, when we mine, when we clear them for agriculture, now we're removing the habitats for these organisms. So we're going to wind up harming the biodiversity in those areas. We'll also see there's additional consequences in terms of climate change with the deforestation. But we're also losing the biodiversity in those areas. And again, with the rainforest, the nutrients in the soil is going to be a big part of that. But just with the rainforest, you can see just a whole bunch of different types of organisms there. So we've got plants, we've got fungi, insects, mammals, reptiles, a whole bunch of different things, just because this area is such a biodiverse hotspot, basically. And then as we move a little bit further away from the equator, or as we move to locations that are not going to be quite as wet, not going to get as much precipitation, what we're going to see is tropical seasonal forests, sometimes known as dry tropical forests. And in certain parts of the year, they may look similar to the rainforest. So during the wetter months, they may look similar because they're going to be that vibrant green. They're going to have a lot of biomass in them. But then during the drier months, they're going to turn brown. So there is going to be a difference between the different environments here. And then with these environments, one thing that makes them sort of vulnerable, at least in terms of comparing them to the rainforest, is that these are more attractive to humans in terms of being a place where they may want to live, because the rainforest itself is going to be more dense, it's going to be more wet, it's going to have more predators, more insects, more parasites, more disease. It's just going to be a more dangerous environment for humans to try to survive in. Whereas the tropical forest, or the dry tropical forest, they're not going to be as wet, they're not going to be as dense, so they're going to be easier to clear. The soil is going to be better for growing crops. So it's going to be better for agriculture. And then it's just going to be a less dangerous environment in terms of predators and disease and things like that nature. So that's why we see throughout the world, these dry tropical forests are very few, very little of these forests remain undisturbed. And we see that within Central America as well as South America. And again, it's just because they are attractive environments for human settlement. All right, and then the next one, so savannas and grassland. These are going to be environments where there's just not going to be enough moisture to sustain a forest at all. So the dry forest, there's at least enough in those wetter months to sustain it through the dry period. The savanna and grasslands, what they're going to have is a more extended dry period, so it's going to be longer. They're going to have a not as wet winter, so they're just not going to be able to sustain the forest, and that's why we're just going to see something like we see here, kind of the just flat grassland. There's no trees there really. They will have some trees, but they're not going to be a full forest, just because there's not going to be enough water, there's not going to be enough nutrients in order to support that growth. And what's common in the savanna, if you think about it, we don't have enough or as much water as the rainforest and things like that, so fires are going to be more common. And then because of that, the plants have actually adapted to survive these different types of fires, so that when the fire comes through, they're still going to be able to survive, reestablish themselves afterwards. And one way they've done that is by establishing extremely long root systems, so that when the fire does come, it's going to burn the top portion of the plant that's above the soil. That part's going to pretty much just die away. But the roots are still going to be intact. They're still going to be surviving underneath the ground. They're going to be able to reestablish that plant, and they're going to be able to reestablish these environments. So they're going to be allowed, they're going to allow the organisms to return, the different grazing organisms. That's going to attract the other predators, and it's going to keep these biomes functioning. And then, like I said, they're not going to be trees in the sense that we're going to have a full forest in these environments, but they do, there will be random trees, and you may have seen a picture similar to this. It's a fairly distinct image, at least in terms of the savanna. It's a very common tree to see, so the umbrella thorn acacia. And just like some of those other plants, it's adapted to survive the high temperatures of the savanna, the low moisture. Some of them, if they're the older plants, they're more mature, they're going to be able to survive frost as well. So these environments will still get cold sometimes. So it's going to be going to need to occasionally survive that frost. And then with the ground in these areas, they can be kind of uneven. They can be tough to kind of get a hold of. So these trees have also adapted to survive in a lot of different types of surfaces. So even very slanted or rocky areas that may be hard to kind of get roots into, these plants have kind of adapted to establish themselves in those environments. And then one thing that's important ecologically about these plants, happens in quite a few plants, is there's actually going to be a bacteria that kind of hangs along the roots of these plants, and it's going to fix nitrogen. So remember from the nitrogen cycle, the atmospheric nitrogen, the nitrogen that's just readily available in the air, that's in the form of N2, so it's 2 nitrogen atoms combined together. That's not a form that plants can actually use, but these bacteria on the roots of this tree are actually going to be able to essentially change that nitrogen into a form that's going to be usable for these plants. And again, that's important because nitrogen, just like phosphorus, is going to be the key nutrients in terms of growth. And then the next terrestrial biome is going to be the desert. So in this case, we're looking at even more extreme temperatures, even longer drought periods than what we see in the savanna. Because of that, we're seeing even more extremely adapted plants. So these are going to be drought deciduous, meaning that in the dry periods, they're going to just drop their leaves and do that as a way to avoid water loss. They're also going to be adapted to flower very quickly. They're going to be great at storing water, such as thinking about a cactus, and they're going to have a thick dermal layer, which again is going to help them retain that moisture. Because in these environments, evaporation, transpiration, just essentially the loss of water through the holes in leaves, that's going to be a pretty common process, and it's going to be a devastating one if these plants don't have these adaptations to kind of counteract them. And then similarly, we see adaptations with the animals as well. So a lot of times the animals will adapt behaviorally to become nocturnal. So they'll sleep during the day when it's hotter, they'll come out at night when it's cooler, so they're not just being scorched by the sun. Similarly, they'll burrow into different locations to avoid that heat during the day. And then some animals have even adapted their excretory system to reduce waste in extremely concentrated waste. And the benefit of that is when they concentrate that waste, they're not losing as much water. So again, helps keep them concentrated, helps retain that water that they need. And then with these environments, they're going to be more vulnerable than some of the other biomes. And it's going to be because they're not quite as biodiverse. There is quite a large amount of biodiversity in these deserts, more than you may even suspect. But because they lack the moisture, They do have more extreme temperatures than a lot of places. It's just a more inhospitable area in general. So these biomes are going to be more vulnerable. And this includes things like livestock grazing or just ATVing. So when I was in Utah, there was like a whole bunch of ATVs that would go around and just kind of different locations and trying to just kick up the sand, run over the little different plants that may be there. And when that occurs, the same thing with the grazing livestock. When they remove those organisms, when they eat the plants or kind of just run over the plants, whatever it may be, what they're going to be doing is, or what that's going to result in is bare soil. And when there's nothing in that soil, when there's nothing there to sort of keep it there, when there's no root systems or anything like that, the soil is just going to become sand over time. And when that occurs, the sand can then be blown just by the wind to different locations. And it's going to be more difficult for another organism to then come in and establish itself in that area. So when we have these sort of events occur, it's just going to make it more difficult for anything in the future to also survive in that environment, because now the soil is just becoming a less favorable environment. And then in addition to that, we'll cover this with the pollution, I think. But in addition to the soil just being able to drift, you'll see in certain locations, if there's any contaminants in that soil, those contaminants are also going to be able to drift when the sand moves. And that also happens in Utah. So the Great Salt Lake is currently shrinking. So it's exposing more and more of the what would previously be submerged lake bed. And then that lake bed actually has cyanotoxins. So when the wind comes through, it's taking some of those toxins and sweeping them up into the atmosphere, into the air. And that could have potential negative effects once those toxins get to other locations, once they're being breathed in by other organisms. And then one thing to note about the deserts, like I said, they are vulnerable by everything's a vulnerable biome, but deserts especially. And again, this is something I saw in Utah down in the southern part near some of those national parks. And then you may see this in different locations as well. But there's something known as soil crusts or biological soil crusts. And essentially, these are just the very top layers of soil. But they're extremely important because they're actually biological communities. There's actually a whole bunch of microorganisms living in those environments. And what they do is they help protect from that soil erosion. So they help protect the soil from moving somewhere else. They allow for moisture to be retained. And overall, they're just improving that environment. They're going to allow it to be a more hospitable environment for microorganisms, for other plants, and just the ecosystem as a whole. But the soil crust, it's a very, very sensitive system. Like I said, it's pretty much just the top layer of soil. And in the very, very top portion of that is where almost all of the biological activity is occurring. So when you see a sign saying, here, don't bust the crust, watch where you step, all of these different types of things, it may seem like a very inconsequential thing. It's, oh, I'm just taking a step off this trail, just one more thing. But when you step on these environments, you're essentially just going to be killing everything there. And like I said, these are very important because they help protect the soil in these dry areas. They help protect these ecosystems as a whole. But also when you step on them, it's going to take, in a best case scenario, it's going to take 5 years to kind of have that system get back to how it was. In the worst case scenario, it can take over a quarter of a millennia, so 250 years or more. So that's why whenever you do see these, you do have to kind of take them seriously because they are very, very fragile ecosystems. But moving from the deserts to a more temperate environment. So the temperate grasslands you can kind of think of as the Midwestern United States, at least in the past. A lot of the grasslands in that area have been replaced with agriculture. But these would be things like the prairies of the Midwest during the expansion of the country, when people started, at least when settlers started moving out to the West. Obviously, there was different Native American tribes and things like that already present there. But this is kind of what you would think of if you ever sort of think about a wagon traveling west towards the Oregon Trail. These prairies would kind of be the central portion of the United States. And in these environments, there's enough rain for grass. It's similar to the savannas almost. There's enough, there's enough rain for grass, but not enough for the forests. And like all environments, we're going to see adaptation. So with those prairies, the long just grass, you see it blowing in the wind. The adaptation of that is just the plants in this environment. A lot of them are going to be pollinated by wind. So it's just going to have the wind actually move those, allow those plants to reproduce, rather than some plants require insects. So that's why bees are so important in a lot of environments. The bees pollinate the different plants. With the grasslands, we'll see the wind is going to do a lot of that work. But like I said, with the grasslands, most of this area has been replaced because it is a very rich soil. So it's very good for growing crops. And because of that, farmers and agriculture use the area just to grow those different crops. And they wound up replacing a large portion of that grassland. And then this is kind of going to be, at least the way that I think about these scrublands, or sometimes you may even hear them called shrublands, just because there's predominantly shrubs in these type of environments. I kind of think of this as sort of an average almost between the grasslands and the deserts, because it's kind of in between those two in terms of the environmental conditions. But we see these in a whole bunch of different locations. So in the United States, we have them in California, and that's where we call them chaparral. But they also occur in Australia, South America, countries like Chile, different places in Africa. So quite a few different locations. And then with these, like I said, predominant plant is just going to be shrubs, just because the soil isn't going to be nutrient rich enough to support large trees and things like that. But because we see all of these different types of shrubs, what we're going to see is a bunch of different herbivores. So just the plant eating organisms, the ones that graze. And then with the grazing organisms, that's going to attract a whole bunch of different types of predators as well. So we will see a fairly biodiverse environment in these biomes, because we've got coyotes, fox, bobcats, just other things, as well as those plant eating organisms. And now what you may be more familiar with is going to be these temperate forests, because Washington, at least Western Washington, is going to be a temperate rainforest. So it's got pretty mild temperatures, not as warm as the Amazon, of course. Doesn't get super cold though. And we do have a large amount of rainfall. So that's why we see the green a lot, because we've got the conditions for a productive environment. And then with these temperate rainforests, we kind of distinguish them between two different types. So deciduous, just meaning that they are going to lose their leaves, so they'll go dormant in the winter. This is more of what I was familiar with back home in New York. So back home in New York, in the winter, everything kind of gets a little bit gross, just because the sky's gray, and then all of the trees and stuff like that are dead. Or at least dormant. So there's none of those, none of the green, none of the fall colors anymore. So it's just kind of a boring, kind of depressing almost landscape. Whereas in the coniferous types of forests, those are going to be the evergreen ones, so the ones that retain their leaves, often needles like we see here. And again, that's kind of what we're looking at in the Pacific Northwest. And then if we go even above that, because remember, we're seeing a lot of these different biomes occur in latitudinal sort of stretches. So we see the same thing going across the globe at different latitudinal ranges. If we go up from Washington into Canada, like I said earlier, we're going to see the one type of forest that's going to stretch across North America. We're going to see the same thing into Europe and Russia. And these are known as boreal forests. Excuse me. And these are going to be dominated by the coniferous trees, so the needle ones, because in these locations, now it's going to be even colder than what we experience here in Washington. And then there'll also be the colder temperatures favor the coniferous trees over the deciduous ones. So that's why we just typically are going to see those present in that type of environment. And then finally, in terms of the terrestrial landscapes, the terrestrial biomes, the ones that occur on land, the final one, we talked about a little bit at the very beginning, the least biodiverse. And the reason for that is because it's going to have the coldest temperatures. It's going to have the least amount of precipitation. So it's just going to be sort of the least hospitable environment for most organisms. Vegetation, so plants are just going to have a difficult time surviving in that environment. And also, we're going to have, for most of the year, we're going to have very, very little sunlight in these environments, at least for the high latitude ones. But we'll also see similar environments at the very, very tops of mountains. And then just with these environments, these tundra, again, very cold, very dry environments. So plants are going to have to adapt specifically for this type of environment. One thing they're going to do is remain close to the ground. So if you've ever seen a picture of a tundra, typically you'll just kind of see a white landscape and it's going to be pretty blank. You're not going to see trees popping up out of the ground, because with those landscapes, with those environments, they're just not, it's going to be tough for plant growth. So one thing they do to survive is remain small. They remain low to the ground. And then what that does is it actually allows for the snow to kind of help insulate them, protect them a little bit from some of the conditions. And then, like I said, in the northern and southern hemisphere, the light conditions are going to be kind of extreme, whereas in the summers, it's going to be light out for pretty much the entire time. Whereas in the winter, it's going to be dark for months on end, basically. So the plants have adapted to reproduce and grow in that very, very short summer window. And then with these plants, since there's not going to be a whole bunch of insects there to pollinate them, these are also like the prairie grass. These are also going to be scattered by the wind. That's going to help them reproduce. That's going to help them move around and keep that population alive. And then the final adaptation, and not all of these plants will have all of these adaptations. Some of them may have one or two. They may have other adaptations as well, but these are just general adaptations we're going to see in this environment. The final one is just going to be darker leaves, and that's going to help them absorb more of the energy from the sun in those summer months. And just like the plants, the animals are going to have to adapt as well. So you're probably familiar with at least a few of these: polar bear, penguin, the fox, things like that. So the most obvious one, if you look, a bunch of these are going to be, they have the white coat, because that's going to help them camouflage into the environment. But you'll also see with some of these animals, particularly with the ones in lower trophic levels, the ones that are going to be more likely to be considered prey, you'll see in the summer months, you'll see them turn brown, because as that snow melts, if they remain white, they're not going to be camouflaged anymore. They're going to be more visible now. They're going to be more easily hunted. So in the summer months, they're going to see their fur become darker, turn to a browner color. And then in the winter, as that snow arrives, they're going to turn back to white to help keep them protected from any predators that may be around. And then in terms of the low temperatures, the shape that these organisms are going to be often is a more advantageous shape in terms of retaining that body heat. So the polar bears, for example, have smaller ears just so they don't lose as much heat through their ears. The animals are going to adapt to have a thick fat layer to help keep them warm. Some of them are going to hibernate just to avoid the extreme cold conditions in the winter, especially when there's going to be limited resources at that point as well. And then other ones are just going to tunnel and burrow just to keep themselves out of those conditions when possible. So they'll use the snow similar to the plants, just to sort of insulate and protect themselves. So that was the terrestrial. So looking at the land-based stuff. Now we're going to move into the marine environments. So with the marine environment, we're thinking about saltwater environments typically. So oceans and seas, things like that. We'll look at freshwater environments at the end. So we'll look at rivers and lakes and things like that too. But just like the terrestrial landscapes, the terrestrial landscapes are reliant on plants and things like that, the photosynthetic plants to provide sort of the basis for the energy, provide the basis for that community. The same thing's going to be true in these marine environments. Oftentimes with these, what we're going to be looking at is things like algae or phytoplankton, which are kind of just little very tiny small plants that are just floating around there. And where we're going to see these occur a lot is going to be near the coastlines, because just like the plants, these photosynthetic organisms are also going to need nutrients. And what we're going to see at the coastline is we'll often see some of these nutrients just wash off into the water, so into the ocean or sea, whatever it may be. We'll see those just come from the land, whether it's due to agriculture, just natural presence of whatever those nutrients may be, dumping them. We'll see them kind of make their way from the land into the ocean. And that's why we're going to often see the most productive communities. We'll see them near the coasts. But in addition to the movement of the nutrients from the land into the sea or the ocean, what we're also going to see is a movement within the water as well. So we'll see the organisms as they die, something called marine snow. And it's essentially just as that thing dies, it's going to sink to the bottom. And that's going to provide nutrients for the communities lower down in the water. But what we're also going to see is there's going to be currents that help bring some of those nutrients back up. And that's going to help provide for the surface communities as well. So we're going to see sort of the nutrients move up and down throughout these levels. And then with the marine environment, we do have sort of distinct layers. And with these layers, we're going to see differences in temperature, salinity, so the amount of salt dissolved in those in that water, the density of the water, and it's also going to be affected by the amount of light that's present. And if you just think about it, as we move further and further down in those water, we can see it in this picture. It's just going to become a darker and darker environment, just because the light is going to get absorbed by that water. So we just won't have as much of it making it into the lower environments there. And then with the light, the very top layer of the ocean is known as the photic zone. So photon just refers to a light particle. So photic zone is just the light zone. And then we've also got different names for these different layers as well. So the first three are grouped together into the pelagic zone. So we've got epipelagic, mesopelagic, and bathypelagic. And those prefixes just mean top. So epidermis, the top of your skin. Epi just means top. Meso, middle. So we've got the middle layer. And then the final one just at the bottom there. And then even below those, we've got kind of the sort of even funkier layers of the marine environment. And that's where we're going to see kind of the extremely odd and weird stuff start to pop up. So I think the organisms in the marine environment are some of the coolest, but also some of the weirdest. And then with these, we're going to see different adaptations in these different regions as well. So even if they're kind of in the same location geographically, depending on where they are in terms of the water column, so the level of water that they're in, that's going to affect how they adapt as well. So the further down, the less light there's going to be. That's going to require different adaptations from the top. because we're also going to see different temperatures and just different environmental conditions overall. So just like with the terrestrial biomes, a different environment is going to lead to different adaptations. The same thing's going to be true for these marine environments. Depending on where these organisms sort of reside, we're going to see them ultimately adapt to best fit into whatever that environment's going to be. So for example, the anglerfish you may be familiar with, kind of that ugly fish at the bottom that looks like it kind of has the light bulb coming off of it. The luminescent light bulb there is going to attract prey. So it's just going to be a light source. You're not going to see the rest of the fish. You're just going to see that light bulb popping up. And I think it's Finding Nemo that does that. I can't quite remember. But that's going to attract prey because it is in that dark environment. But now if that anglerfish was placed into the trophic or the photic zone, so where we're actually going to have light, that adaptation isn't going to be useful. The other fish are going to see that ugly fish in addition to just that weird light bulb coming off of it, so it's not going to work. And that's why we're just going to see the different adaptations within these different environments. And then in addition to these different layers we have here, we can look at the landscape as well. So as we move from the coast, we've got what's known as the intertidal zone. And that's just looking at the different areas where the low and high tide are actually going to reach. So high tide just goes further into the coast, of course. And then just looking at that, we've got the continental shelf. So this is typically going to stretch out from the coast a pretty good ways, not extremely far. But it's not going to be as deep as the rest of the ocean. And then we'll see eventually we'll hit a point where it is just going to drop off. And that's going to be known as the continental slope. So this is going to be where we start to get into the really deep ocean. And then this part is still deep. So you still have like boats. And obviously, if you've ever been to the ocean, you can't just walk out more than a few feet before you start getting really, before you can't really stand anymore. So just because the scale on this may be a little bit confusing, the continental shelf still is a fairly deep region relative to the size of humans. It's just in relation to the rest of the ocean. It's not a very deep environment. And then with this marine environment as a whole, not a ton is known. And the ocean, for the most part, is pretty bare in terms of biodiversity, just because in a lot of spaces, there's not going to be enough nutrient or biomass production to support other organisms. So there's just not enough of that phytoplankton or the algae, any of those types of organisms to sustain a community. So a lot of times we're going to refer to different locations within the marine environment, different locations within oceans and seas, just as a biological desert, because they are going to be relatively barren. But that's not true in every location. Like I said, around the coastline, where we often see nutrients just wash off from the land, we're going to see high biodiversity there. The same thing in locations where nutrients are just transported due to ocean currents. So you see that in the Pacific Ocean off of South America. You see currents that bring nutrients to different locations. So you see biodiverse communities out in that ocean. And then also there's something unique going on at the very deep portion of the ocean, deep sea vents. Essentially just areas where the molten magma and the core of the earth is just warm, and it's essentially just heating. You can kind of see it here, just heating different environments. We get extremely warm locations here. And what's actually occurring isn't photosynthesis, because there's still not going to be enough light in order for photosynthesis to occur. But it's going to be a similar process in which these organisms are producing energy from chemical reactions, oftentimes from sulfur-based compounds in these vents themselves. And that's going to help communities survive in those environments. So with the deep sea vents, we'll see a lot of microorganisms are typically going to be there, because they're going to be able to produce energy from the chemosynthesis, excuse me. And that's going to help support those other organisms that may be present there. But again, that'll be typically the microorganisms we're going to be focused on in that type of deep sea vent community. But like I said, the shoreline typically going to be where we see the most biological activity, at least in terms of this type of diversity that we're really thinking of in terms of an environment. And then what we're looking at in this picture is going to be a coral reef. So we'll talk about that a little bit in the second part, sort of the challenges that coral reef face, because they have been impacted pretty drastically due to environmental changes like ocean acidification from climate change. But these reefs are very important because they do provide shelter for other organisms. And like I said, these communities are going to be present. We're going to often see these communities near shores just because that's going to be where we have the nutrients present. But with the reefs specifically, they can't live in an area of extremely high nutrients, just because when there's extremely high nutrients, what we're going to see is excessive algae growth. And then the algae is essentially going to basically just block out the reefs from the sun. But with these shorelines, what we're going to see is they're kind of under attack's not the best word, but they're in danger, because what's happening is a process known as hardening. So you can see it here. We're building structures to help protect the landscape from waves and different things like that. We're doing it for property reasons. We're doing it for just a whole bunch of different reasons. And it's essentially just introducing man-made structures into these environments. And the reason that can be the reason that can negatively impact these environments is because it's going to negatively impact the biodiversity of these areas. It does have benefits, like I said, in terms of the property sort of structure that a person may want with their home or their business, something like that. And it does help absorb some of the shock and some of the damage that can arise with large waves. So things like tsunamis and stuff, sometimes they need to kind of build in certain hardened structures. But generally what we want to do to protect these shorelines is what's known as a living shoreline. And you can kind of see it on the left-hand side here. What they're going to do is use rocks, they're going to use plants, different organisms, and just basically build a little community there, rather than a living community, like it says, a living shoreline, rather than just place some structure in. And then with these communities, like I said, the hardened structures are usually used to help prevent damage from waves and things like that. These living communities, in addition to providing biodiversity, improving biodiversity by providing that habitat, they help keep the water clean, because some of these plants can actually absorb some of the pollution that may be in that water. But they're also going to provide some of the protection from those waves. I'll admit it's not quite to the extent that a lot of these hardened shorelines can protect, but it does do a pretty good job, and it does provide those additional advantages as well. So like I said, the shorelines, the storms is a big reason, but we can get some of that benefit with these living ones, while also maintaining the environment, maintaining those ecosystems. All right, so this will just be, I didn't put it at the top, but this will be where we start to look at freshwater systems. Oh no, there it is, okay. A little bit, because this is going to be, estuaries at least are going to be kind of a mixture of fresh and salt water. And the reason for that is because this is going to be where we see rivers empty out into seas. So look at the mixture of those two types of water, those two types of environment. And then due to that, we're going to see extremely biodiverse regions when we have an estuary. And we'll focus a little bit more on the estuaries in part 2 of this, when we kind of see some of the damage that happens to these ecosystems and how we can kind of protect it. But just remember, estuaries are going to be extremely biodiverse because we have extremely high levels of nutrients, along with the warm and sort of calm water that's going to help promote that growth, help promote that biodiversity. And then these tide pools, final thing with the marine ecosystems, if you look, you can kind of see what's going on. These are going to be rockier areas where sometimes they'll be completely submerged under high tide, but when low tide, when we're at low tide, you'll see some water still present, but you could kind of walk around here. Because of this, it's going to make it a difficult region for a lot of things to survive, just because they're going to see pretty drastic changes in the environment between high and low tide. Because if you think about high tide, you're going to be in a extremely wet environment. And then in low tide, you're going to be in a much more drier environment. But that drier environment is now also going to leave you exposed to higher temperatures just due to more sun exposure. So it's going to be difficult for a lot of things to survive in this area. But the things that can, just like most organisms that have adapted to their environment, the organisms that have adapted to this specific environment, this specific type of biome, are going to be extremely well adapted for it. And then finally, we're going to look at the biomes of the freshwater ecosystem. So again, lakes and rivers. With the lakes, the quality of that lake is going to be affected by a whole bunch of different things. So obviously, if we just dump pollution into it, that's going to be a problem that's going to negatively impact the lake, that's going to negatively impact the organisms living in it. But in addition to stuff like that, we just want to think about the natural availability of nutrients. One thing you may not consider is how much stuff is suspended in that water. So if you think about if you've ever kind of just been walking around shallow water and you kick up some of the sand, you see that water gets much dirtier, much cloudier when we've got that suspended material. If you're in a lake where that's sort of a more natural, a more constant state, that it has that dissolved material in it, suspended material, I should say, rather than dissolved, when it's got that suspended material. Now the light's not going to be able to make it as far into that water. That's going to affect the amount of plant growth. That's going to affect the entire ecosystem as a whole then, because that's going to also affect the amount of oxygen present in the water. That's going to impact what type and how much of different organisms can survive. Depth, of course, that's going to influence, again, the light penetration. Deeper lakes are going to have darker environments at the bottom. It's also going to affect the temperature, which we'll see in a little bit, which is the next point. 5, currents, just the movement of the water, the distribution of nutrients and things like that. The composition of the lake. So if it's a muddy lake bottom versus a rocky lake versus a sandy lake, we're going to see that those are also going to have different consequences in terms of what types of organisms may be living at the bottom of the lake, as well as just sort of the environmental conditions that may be related to whatever those different substances are. And then with these, just remember all of these, just like pretty much everything in this course, everything is going to be interconnected. So like I said, depth and temperature are clearly very closely related. The same thing with the suspended matter and temperature. The amount of light that's being absorbed is going to affect the temperature. The composition of the lake is going to affect the temperature. So all of these are going to be interrelated. And then finally, connections to and isolation from other aquatic and terrestrial ecosystems. One thing with this is acid rain. So ecosystems that are in areas that have large amounts of limestone in the bedrock are going to be better able to handle acid rain than areas that don't have as much limestone. So if we have this lake here, for example, if the bedrock did contain limestone, some of that limestone would get into the water and would allow the water to essentially handle at least some amount of acid rain. Whereas if it wasn't, the water would quickly become acidified in the presence of acid rain. But like I said, the depth of the lake is going to be important because that's going to affect the different temperatures we see. And we're actually going to see, similar to the marine environment, we're going to see different layers actually pop up. And this is going to be true if it's a deep enough lake. So if you think about it, if you've ever been just in shallow water, it's more or less going to be uniform throughout because the sunlight's going to be able to travel through the entire thing. But if you've ever been swimming in a deeper lake, especially if you go underwater, you may hit a point where the temperature quickly sort of changes. That's going to be what's known as the thermocline. So thermo, just in general, means heat. That's going to be the spot where we'll really see the temperature change. And then with this, what I want to point out is this is saying summer here, because the exact layering of these lakes is going to be dependent on exactly what season we're looking at. And we can see this kind of present here. So we're looking at the top left to start, same exact thing we just saw. It's just in this case, we're kind of given different temperatures to these different environments. So you can see at the surface, 22 degrees Celsius. As we go down, it starts to decrease a little bit, but then we hit that thermocline, that area where the sunlight's no longer reaching. We're going to see a drastic change in that temperature. And then once we do that, we just have a gradual decrease again from 8 to about 4 degrees Celsius at the bottom. And then as we transition from summer to fall, just think about it, the air temperature is going to decrease. So the temperature of the surface water is going to decrease. And eventually we're going to get to a point where it's even throughout, and that's going to cause the water to actually start to mix. We're going to see this turnover process because, again, we've got uniform temperature throughout, so it's just sort of, we're just starting to see it mix now. And then as we go fall into winter, again, we're seeing the air temperature drop. What we're going to see, though, is that that's only going to affect the top portion of the lake, because water has the unique property where solid ice is going to be less dense than liquid water. So we're actually going to form the solid layer on top. And that's going to actually insulate the lake. So what we're going to see is the bottom is still going to remain 4 degrees. It's just going to get cooler as we go to the top. And then again, as we transition from one season to the next, this case, we're actually going to be heating up the air because we're going from winter to spring. So we're going to have the lake start to thaw. That's going to heat up the top portion of the lake. And again, we're going to start to see that turnover. So during the spring and fall, when we start to see, you can kind of think of those as seasons of change. That's where we're going to actually see the water really start to move around. We're going to see it start to mix. And then in summer and winter, we're going to see the clear layeration, stratification of the temperature of that water. And then in addition to lakes, which of course provide a whole ecosystem in itself for a whole bunch of different organisms, we've also got things that are known as wetlands. And then these wetlands are going to be important. Well, first, what they are is just going to be an ecosystem that is at least partially throughout the year is going to be submerged or saturated. So you can see, depending on exactly the conditions, we've got slightly different names for the different types of wetland. So bog versus fen, marsh versus swamp, depending on the exact conditions, the exact type of vegetation that's present. But in all of these, we're going to see similar sort of, at least with wetlands, I just think of swamp in general, just as the term. It does refer to something specific, but you can see kind of the characteristics here of just extremely wet, and that's going to help promote the biodiversity within these areas. And because of that, it makes them extremely, extremely important. I think in the textbook, it said that 5% of the United States is wetlands, I believe. But within the wetlands, they support 1/3 of all endangered species within the United States. So of all endangered species, or if you just pick 3 endangered species, at least one of them would likely live in a wetland. So protecting these habitat is going to be extremely important in terms of protecting those endangered species, the species that are currently at risk of going extinct. But in addition to protecting those different types of organisms, specifically birds, so a lot of migratory as well as breeding birds live and habitate in the wetlands. But in addition to protecting those organisms, wetlands also serve a tremendous importance towards humans, because what they do is they allow for reductions in flooding, because they're going to essentially just absorb some of the water from the environment. They're going to be able to take on some of that water rather than have it making its way immediately into places where humans live. And that's a tremendously important economic benefit. Saves the US 3 to 4 billion per year. And that's in terms of money that would normally have to be spent on fixing damages caused by flooding. And then in addition to that, the different plants, as well as some of the bacteria that live in these wetlands, actually help purify and filter the water. So the different pollutants that may be present are actually going to be taken up by the roots of the plants, are going to be taken up by the bacteria, and they're no longer going to be present in that water. So it helps keep it clear for the other organisms, the other birds that might be drinking it. Oops. All right. And then okay, so that will be the end of part one. Part two, we're going to look at kind of what's threatening these different biomes, what that ultimately can lead to. And that's going to be a little bit depressing, but we will also end it with what has been done to kind of help preserve these biomes, preserve this biodiversity, and then as well as what can be done going forward.